Up next, excited to introduce our next speaker. She completed her PhD from Cornell University. She was named Forbes 30 Under 30 in Science and 30 Under 30 Rising Stars in AI, and also JP Morgan Early Career Outstanding Faculty. Wow, sorry. She currently serves as Assistant Professor, University of Wisconsin-Madison. Please give a warm welcome to Sharon Lee.
Thank you, Artie, for the kind introduction. It's my great pleasure to be here at the Future of Data-Centric AI event. And today I'll be sharing with you some of our recent work on uncovering the unknowns of deep neural networks, and I'll be talking about some of the interesting challenges and opportunities in this problem domain. And so now let's dive in. I would like to start the talk by showing you this video. And this is a model trained on the Berkeley Deep Drive 100K dataset, performing bounding box tracking on the road. And needless to say, deep learning has achieved pretty remarkable success in many exciting areas like this. And I personally feel very fortunate to witness the many breakthroughs since I started my research journey many years ago. And today, instead of adding more praises, I would like to encourage you all to maybe take a step back and have a more critical look at the methods and technologies that we built. And hopefully by the end of the talk, we can see things in a more well-rounded perspective. I know there are many experts in statistics, machine learning, and AI in the audience. So let's think for a second how you would approach building and deploying such a self-driving car model. And so the typical process is to start collecting some training data with corresponding labels. And so here I'm simplifying things a bit. And then train on your favorite machine learning model. And the output typically contains some predefined categories such as pedestrian, cars, and trucks, and so on in this case. And of course, there are thousands of other details to sort through. But let's say once you finally have a model with decent performance and you think it's ready to deploy, more unexpected work has just begun. And why do I say that? Because the classic assumption that you've learned from Machine Learning 101 is that the training and test data distributions match each other. And this assumption rarely holds true in reality, which was also covered in the previous talk from Professor Anima. And so in the real world, it's closer to this open world setting where a lot of unknowns could emerge. And so for example, we took this image from the MS COCO dataset and run through the self-driving car model that we just trained on the BDD dataset. And you see that the model can actually produce quite overconfident predictions for this unknown class, cow, which was never exposed to the model during the training time. So in other words, deep neural networks do not necessarily know what they don't know. And this has raised significant concerns on models' reliability because algorithms that classify these out-of-distribution samples into one of the known classes can be catastrophic. For example, think about in healthcare, a medical machine learning model trained on a certain set of diseases may encounter a different disease, and it can cause mistreatment if not handled cautiously. And this issue is prevalent not just for high-stake domains I just described, but also in many other scenarios where machine learning is being used on a day-to-day basis. So this is another example that I really like. Imagine you're developing an app of a food image classifier so that a user can go to a grocery store and snap a photo to get some recommendations on the recipes, which could be very useful. And for those of you who have worked extensively with users' data, you would know how diverse and unpredictable it can be, right? There could be a lot of images other than food. And this is precise the type of messy but fun data that I spent quite some time working with back in industry. And so my time working with this real-world machine learning models and data has given me a firm belief on how important this following problem is. How can we build unknown-aware deep learning models for reliable decision-making in such an open world? And one important step towards this goal is to be able to detect out-of-distribution data. And so what is out-of-distribution data, you might ask? Let me first provide a simple view on this. And so let's say we have our training data distribution that is a mixture of two Gaussians for a class label y equals to 1 and y equals to -1 in this case. And so our in distribution Pn would be the marginal of this joint distribution defined over the input space x times the label space y. And now during the deployment time, these orange dots could emerge, which are out of distribution from an unknown class that is other than green versus blue, and therefore you don't want the model to predict this to be either y equals to 1 or minus 1. And so to translate this toy data into some higher dimensional images, you can think of, for example, CIFAR 10, which is a common computer vision data set as in distribution, and SVHN on the right side as OOD, which have disjoint labels. Well, you might think that this OOD is way too obvious to us human beings, but I'm going to show you how such an easy setup could trouble these state-of-art neural networks. And later on in this talk, I'll discuss how we can go beyond such simplified definition. And so for now, let's stick with this simple view. And so SVHN is just one of the OOD that the model would encounter. And there are, of course, many other unknowns on this complex data manifold. And this is an image from a recent talk from OpenAI, which I think really nicely illustrates this complexity of the problem. And so out of distribution detection is indeed a hard problem. And let me explain why before we attempt any solution on this problem. And so the first challenge is the lack of supervision from unknowns during the training time. And so typically the model is trained on the in distribution data only. In this case are the green and blue dots using our favorite empirical risk minimization. And so you can't really anticipate where these orange dots could emerge in advance because there is a huge space of unknowns, especially in the high dimensional space, right? So what we're showing here is just in 2D. And you can think how complicated things quickly become as you move to this high dimensional space. And so this problem is further exacerbated by this high capacity neural networks that we're working with nowadays. And so in this plot, if you look at the decision boundary, which is right in the middle, which tries to distinguish between two classes, orange versus blue, you can see that the decision boundary undesirably includes and covers some of the OOD data, which is in red dots here, right? So it's on the same side as these orange dots. So it would be classified as orange during inference time, which is undesirable. And you might, ask, why don't we perform density estimation using deep generative models? And it turns out there are unique challenges too. For example, the generative models could be quite difficult to optimize. And even if you can train it to converge, there's a very interesting study by Eric Nellis-Lake showed that OOD data can, in some cases, trigger higher likelihood compared to ID data. So at least for now, the performance of generative-based approach often lag behind the discriminative approach. And so for this talk, I'll stick with the discriminative-based approach. And so over the years, there has been really a lot of exciting progress made on OOD detection, in particular for deep neural networks. And here I've highlighted a few representative ones and also including some of our recent contributions in gray. And so the earliest work adopted this post-hoc approach for OOD detection. And let me give you a method overview. And so typically the model is trained on the in-distribution data, say CIFAR 10, using empirical risk minimization. And now let's take the network as it is without modifying its parameters. And so during inference time, for any given input, we're going to devise a scoring function, S of x, for OOD detection. If it's below the certain threshold, we're going to reject this input. And otherwise, we produce the class prediction as usual. And so the advantage of post-hoc OOD detection is that it doesn't really interfere with the original model or the task, especially if it's already been deployed and running in the production and so on. And so an obvious baseline is to use the softmax confidence score, which is the largest posterior probability, P of y condition on x, among all these classes. However, it doesn't really work well because, as we saw earlier, neural networks tend to produce quite overconfident predictions, and therefore you see this, areas that is heavily overlapping between the in distribution versus OD, right? Concentrating on this, the high confidence region. And so our early work on ODIN was one of the first to address this issue by using the temperature scaling and input preprocessing. And mathematically, we can show that a large temperature has a strong smoothing effect and will make the softmax score distributions more separable between the two types of data. So here denoted in green versus gray. And so you can see this effect on the left side. And so in hindsight, what ODIN really tries to do is to push these confidence score back to this logit score. And I do want to highlight here that the score produced is no longer probabilistic, which is desirable for OD detection, but may no longer be meaningful from a calibration perspective. And so that's two different tasks I do want to kind of highlight. And in our recent NURBS paper, we took this one step further and proposed an energy-based OD detection framework, which leverages the energy score derived from the output logit of this neural network for detection. And so now I would like to dive a bit more into the details here. So energy-based model has been around for a while. And so to give you some background, an energy function takes an input x, say my cat, and corresponding label y. And then it will produce a scalar called energy. And this function can be non-probabilistic. And if you want to turn this into a probability density, you can do so using the Gibbs distribution. And so again, this is the same equation that I just showed. And if you look at this denominator, which is also known as the partition function, which takes the integral over all the possible y's. And by equalizing these two sides, we can derive the energy E of x for any given input in terms of this formula. That is the negative of the log partition function. And so this notion has been around in physics for a long time. And so how is this energy-based model related to neural networks? It turns out a neural classifier can be interpreted from an energy-based perspective. And so, for example, let's consider a neural network, in this case, producing output logits f1x, f2x, and so on. And after softmax, it would produce a normalized probability density, P of y conditional on x. So here is the definition of softmax, which you're already familiar with. And so now if we define energy function E of x comma y to be the negative of the logit output, effectively this turns into something that we just saw earlier. And so now recall this is how free energy is defined. In the context of a neural classifier, this free energy replaces the integral with the summation across k discrete classes. And now for every input and a pre-trained neural network parameterized by theta, you can calculate this very conveniently using the log sum exponential operation. And so in this work, the key idea is to replace the softmax confidence score with the energy score for OOD detection. And so with energy scores, the distribution now become much more separable. And in particular, the in distribution no longer have the spiky distribution that we saw earlier. And notice that in the x-axis, we flip the sign to use negative energy score, which, to align with the convention that larger score indicates in distribution and vice versa. And to evaluate our approach, we train, in this case, a model on Cypher 10 as in distribution and evaluate on SVHN as OOD. And so here we measure the performance in terms of FPR 95, which is the fraction of OOD that is misclassified as in distribution when, let's say, 95% of in distribution is correctly labeled. And so we want this metric to be as low as possible. And so if we use softmax score, this FPR is roughly around 48.87. And in contrast, using energy score can reduce this FPR substantially to 35.67. And so we tested thoroughly on more data sets and consistently observed a significant improvement. And so this is again, on Cypher 10. And the blue bars are softmax score versus energy score in gray. And I do want to highlight that this advantage of energy score is it's very easy to use, and it doesn't require any hyperparameter tuning whatsoever. And going beyond this empirical performance, we also provided some theoretical explanation for why softmax score is suboptimal for OD detection. And in order to explain this, we can first look at the training dynamics of neural networks in terms of how they change the energy state of the output. And so here is our standard cross entropy loss for classification. And you can take the negative of the log probability corresponding to the ground truth label. And now we can derive this gradient of the loss with respect to the parameters. You can skip all the details, but what I want to highlight is that the training dynamics essentially push down the energy for our training data, right? So E of X is going to be lower for in distribution. And so now if we look at the softmax score, or precisely the log of the softmax, it can be decomposed into two terms, the energy plus the maximum logit. And recall that the first term is going to be lower for in distribution, and the second term is going to be actually higher for in distribution. And so this summation overall results in a biased function that is no longer aligned with the data density for OD detection purposes. And so if you're interested, you can check out our papers for detail. We also have a work coming out that bound the performance more rigorously. And so another interesting, nice thing about energy-based framework is that it not only works for the multi-class classification, but also other family of machine learning tasks, such as multi-label classification problem. And this is the recent work in collaboration with Sharon, Weitan, and Alex. And so to motivate the problem, previous studies have primarily focused on this detection in the multi-class setting, where each sample is assigned to one and only one label. And this can be quite unrealistic in real world. For example, if you look at the photos on your phone, most likely, each photo can have multiple objects of interest, right? And also in the medical domain, multiple abnormalities may be present in a medical image. And so the main challenge in the multi-label setting is how do we estimate uncertainty by jointly leveraging the information across different labels, as opposed to just relying on the one dominant label. And in the case of multi-label, you can't really even tractably estimate this likelihood because it requires the sampling combinatorially across different labels. And so this problem is actually harder than multi-class. And so we propose this novel scoring function that takes into account the joint uncertainty across labels and also provided some mathematical interpretation from a joint likelihood perspective. And in particular, JointEnergy takes the summation of label-wise energy score. And you can imagine having multiple dominant labels is indicative of in distribution and vice versa. And despite its simplicity, we show that JointEnergy can be surprisingly effective and also has this joint likelihood interpretation. I'm not going to the details here for the time being, but just to maybe quickly highlight on the experimental side that JointEnergy actually works quite competitively compared to the previous baselines. So I would like to use maybe the remainder few minutes sharing some of the parting thoughts. So in this talk, I've talked extensively about post-hoc OD detection methods. They're quite powerful, But I think there's a need to move beyond that. They're not sufficient to mitigate this problem of OOD because they don't fundamentally change how the model is trained, right? So if you think about existing learning algorithms, they're primarily driven by optimizing the accuracy on the in-distribution data. And so you can see it as in the middle plot, the decision boundary can actually overshoot and produce overconfident prediction, even though it can discriminate among those three classes pretty well. But they're ill-fated for OOD detection purposes. And therefore, we need training time regularization to explicitly account for the uncertainty outside the in-distribution data, right? So the ideal decision boundary should be something like maybe the right side, which is more aligned with the in-distribution data density. And so one way to achieve this is using our proposed energy regularized learning, which have this dual objectives during the training time. One for classification using the standard cross entropy laws. And so this minimizes the risks on the known data set. And the second term is intended to minimize the risk for the unknowns. And so this regularization essentially shapes the energy surface explicitly using the squared hinge laws and tries to make the energy, as separable as possible between the two types of data, right? So we have this, the first margin, the first loss tries to pull down the energy for the in-distribution data, and the second term tries to push, the energy to be high for OOD. And so the result of this training is stronger separability measured by the energy score, as you can see on the rightmost plot here. And in contrast, the left two plots are based on the post-hoc methods. One uses softmax score, and another one uses the energy score, and both are derived from the pre-trained neural networks. And you can see that the performance gain is actually substantial, reducing FPR down to 1% ish. And so here I just want to show, evaluation more comprehensively on different test data sets. And the orange bar is when we, employ this regularization during the training time. And our work is also open source. Here is the GitHub link if you're interested in building further and create, even better, stronger solutions on top of it. And moving forward, I think there are great future opportunities when it comes to learning algorithm design. For example, as I mentioned, we really need algorithms that essentially tries to learn a more compact decision boundary that not just care about the in-distribution data, but also the potential risks associated with the unknowns. And you can think of, for example, in this figure, that this black dashed line tries to wrap around our in-distribution classes while performing the in-distribution classification. And this is the recent work if you're interested in checking out our papers. And aside from learning algorithm design, there are also great opportunities to think about how we consider and evaluate a more realistic data model. The current evaluation, as I mentioned, can be too simplified to capture some of the nuances of the problem in the real world. And I'll give you an example here. And so, for example, a lot of the existing work, are evaluated on the common benchmark, CIFAR-10, which contains low-resolution images of site 32 by 32 with a handful of classes. In these methods that work well on CIFAR-10 may not necessarily translate into a real-world setting where we have a lot more visual categories. And as it turns out, OOD detection performance can decrease quite rapidly as with the number of classes increase. And this is because, again, the decision boundary quickly becomes a lot more complex. And so our recent paper develops a group-based OD detection framework that tries to bridge this gap. And so as you can see that in this plot, the blue curves are using our method, which scales more effectively to the large-scale data sets, say ImageNet with up to 1,000 classes. And as part of the paper, we also released this new benchmark based on ImageNet. And here's the link if you're interested in, creating even better solutions on top of this. And so I think we're almost out of time. I just want to maybe keep this part short. Another interesting research question to think about is how do we actually formalize this notion of, OOD, right? And I think some of the previous speakers has kind of talked about there could be a lot of issues in our training data, and one is, potential bias and spurious correlation in this case, where the bird species is often correlated with the background. And so what we found is that, when the model is trained with this bias that crept in, it actually would manifest in the downstream OOD detection. For example, the spurious OOD that have the same or similar background information but with a different semantics can be really difficult and challenging to be detected. And so it's important to model this data shift by taking into account both this invariant feature as well as the environmental features. And just to quickly recap and summarize, so today I've started my talk with the post-hoc OOD detection methods, and we've covered some of the common OOD detection score, including softmax score, ODIN, and so on. And energy score further improves on the previous method, and which is also very easy to use and hyperparameter free. And moving forward, there are opportunities of moving beyond these post-hoc methods and thinking about how do we, regularize the learning to minimize risks on both the knowns and the unknowns. And lastly, I've also talked about opportunities for more realistic OOD detection tasks, such as moving beyond Cipher 10 to larger benchmarks. So with that, I would like to conclude my talk, and thank you all for listening and being here. I'm happy to take questions if there's any, and if we have time.
Thank you so much, Sharon, for that wonderful presentation. Such an important topic, and it's widely applicable. People enter stuff in chatbots, usually out of distribution or could be out of distribution, as well as, of course, medical imaging. And it's really important to catch these cases such that you can reliably deploy your models. So very, very important topic. Thank you for sharing your expertise there with us.
Thank you, Artie.
Unfortunately, we don't have time to get to all the questions. We'll just stick with the one that got the most upvotes. But again, we will be making note of these and then sending them to Sharon, as well as addressing them in the chat if you have time, Sharon, to stay on. So the top question is from Sebastian. He says, out of distribution detection seems like it's a great way to detect useful data to label. Do you think those high confidence misclassified classes highlight the limited generalization of current models, or how are those two concepts related?
Yeah, that's a really great question. Thank you, Sebastian. As I mentioned in the second part of my talk, I think this fundamental issue of neural networks producing overconfident predictions on this potential OOD data is rooted in how limited the current training objective is, solely focusing on optimizing the classification accuracy without really taking this explicit account of unknowns. And so that's why I think it's very important for the research field moving forward to think about how do we design a training algorithm in a way that factors in both the risks for the known part, which is in distribution, and also unknowns. And so we need that dual objective in this learning algorithm design.
Makes sense. Thank you so much, Sharon, for joining us today. And we will be sending you the rest of the questions that unfortunately we won't have time to get to. But again, thanks for taking the time.
Thank you.